Okay, let's continue our discussion at 2.8 here. We got one more topic to look at, and then we'll look at some examples. 2.8, the last thing we want to talk about is higher derivatives that they talk about on page 163. And by higher derivatives, we just mean being able to take the derivative of a derivative. If we have y equals f of x as a function, well, then we can find a function f prime of x by taking the derivative of the original function. But why can't we take a derivative of that? Why can't we take a derivative of this function to get f double prime of x, and so on? In fact, we could keep going and take really as many derivatives as we are allowed to do, f triple prime of x, and so on and so forth. Remember, in the first lecture we had a function y equals f of x, and it was equal to 2x cubed plus 3x. And we found by our limit definition that f prime of x was equal to 6x squared plus 3. 6x squared plus 3. Well, let's go ahead and find f double prime of x. And what we're going to do then, that's going to be the derivative of f prime of x. So let's do that. F double prime of x is going to be the limit as h approaches 0 of f prime of x plus h minus f prime of x divided by h. Okay? So the function here is f prime that we're putting in an x plus h and an x to find this difference quotient. Well, that's going to be the limit then as h approaches 0. Let's see, f prime of x plus h. Well, f prime was 6x squared plus 3, so we'll have 6 times x plus h squared plus 3 minus f prime of x. Make sure you put that in parentheses, so minus 6x squared plus 3. All that divided by h. All right. So we'll get the limit then as h approaches 0 of, let's see, we're going to have 6 times, if we square out x plus h times x plus h, we get x squared plus 2xh plus h squared. So 6 times that quantity plus 3. Let's go ahead and distribute that negative through there to get minus 6x squared and minus 3. All that over h. Now let's go ahead and distribute the 6 through this quantity here to get the limit as h approaches 0 of 6x squared plus 12xh plus 6h squared plus 3 minus 6x squared minus 3, all divided by h. We should lose all of our terms that don't have an h in them. Positive 6x squared, negative 6x squared, positive 3, negative 3. And so we're left with then the limit as h approaches 0 of 12xh plus 6h squared. Looks like that's it, all divided by h. Now if we divide both of these terms here by h, we get 12x plus 6h. And actually we want to take the limit of that as h approaches 0. So the limit as h approaches 0 of 12x plus 6h. And now if you plug 0 in for h, since this is a continuous function which is defined at 0, we get 12x. And that is, remember, f double prime of x. F double prime of x. Let's go ahead and graph that with the original function and the derivative to see if we can see a relationship there. So remember that the original red function was our function f of x, which was, let's see, what was that? 2x cubed plus 3x. Then the derivative function, 6x squared plus 3, was graphed. Now we have 12x, and we want to graph that. That should just be a line, and you can see that it is. Now remember, this green line is the derivative of the blue graph. The derivative of the blue graph. So if we look at the derivative of the blue graph, well, when x is negative, our function is decreasing. Function is decreasing. The line tangent has a slope which is negative. That means the y values of the derivative function f double prime are going to be in negative territory. But they're increasing and heading towards 0. Why is that? Well, when x is equal to 0, this blue graph has a derivative that is 0 because the line tangent is flat. And so the slope is 0. So the derivative value of the blue, which is the green, is 0 there. Now what happens as the x values increase? You can see the derivative increases because the line tangent gets steeper and steeper, and so the derivative values there, f double prime of x, also increase. So if you think of the green as the derivative of the blue, it makes sense. Let's look at another example to help illustrate this point. Let's look at number 37. You can see in your book you have a graph where 3 graphs are given. Actually, 3 functions. The graphs of 3 functions are given, a, b, and c. We're trying to decide which one could be f, which one could be f prime, and which one could be f double prime. Okay, so which one is the derivative of which? Well, let's take a look here. Let's look at the original function c. Um, yeah, what we see is that c has a couple of places where the derivative would be 0. A couple of places where we would have a derivative that's 0. One would be right here and one right here. So if a or b are the derivative function of c, then their y values at these 2 points would have to be 0. And you can see that is maybe the case for a in this first one. It looks like where the derivative is 0 here, the a value is 0, but that's not the case in the second one. Here the derivative has to be 0, the derivative function of c, but a is not 0, b is not 0 either. So I don't think that a or b are derivatives of c. Alright, so let's see what we can do then. How about let's look at another function where the derivative becomes 0. And let's see, at b we have the function b, the yellow graph. There's a derivative of 0 here where the line tangent is flat. And you can see that c has a 0 value for its y value at that same point. Also, as b levels out here, the c value heads towards 0. As b levels out, its derivative is getting closer and closer to 0 because the curve is flattening out, and you can see the c value is heading closer and closer to 0. So it appears to me that c is the derivative of b. c is the derivative of b. Now, what can we find then? Is c or b the derivative of a, or is a the derivative of one of those? Well, what you want to look for is relationships between when a function is increasing, when another function is positive, and so on. Remember, the relationship between c and b, when b is decreasing, c is in negative territory. Let's look at a. A is increasing in this whole section right here from about this point, well, all the way up until about this point right here. A is increasing. Well, notice that b is in positive territory for that entire section. Where A is increasing, b is in positive territory. Now, as this function levels off and the derivative becomes 0 at about right here, you can see the b value, the y value of your b function becomes 0. b crosses the x-axis. So that function has a value of 0 there. And then it becomes a little bit negative here. The derivative of a becomes negative since a is decreasing here. And you can see that b becomes negative in that same region. So it looks to me like b is the derivative of a. So that means that a is f of x, b, which is the derivative of that, is f prime of x, and c, which is the derivative of that, is f double prime of x. So it takes a little bit of thinking. It takes some, just got to walk through it and just remember the relationship between a derivative and its original function. Alright, and then just continuing a little bit with our discussion of higher derivatives, we want to talk about that special case when s of t is some position function. So if you give me the time t, the function s tells me the position of a particular particle or an object or something like that. Well, we've already talked about the velocity function being the derivative of the position function because that's telling you how fast you're changing. By the way, the absolute value of this velocity function is the speed. That's just a number. But the velocity function could be positive or negative, which tells us not only how fast it's going, but which direction it's traveling. Alright, and if we take the derivative then of the velocity function, which is going to be the second derivative of the original position function, that's going to give us acceleration. So the acceleration is just what you expect it to be, how fast your velocity is changing. So the acceleration is the derivative of the velocity, the second derivative of speed, and so you get a change in velocity by acceleration. And then finally the jerk, which we could sometimes write as j of t, is the second derivative, well actually it's the derivative of the acceleration, which is the second derivative of the velocity, or the third derivative of the position function, and that is the jerk function. And if you step on the gas, you're changing your acceleration quickly, you feel a jerk in the car, so that's why it is called that. So you can see that we can have a triple derivative here of the position function. By the way, if you want to take a fourth or higher derivative, first three derivatives we use these marks up here, but a fourth derivative we would use, say, s, and put a 4 in the superscript, but in parentheses. We're not raising it to the fourth power, we're taking the fourth derivative. That's the fourth derivative of s. And so any derivative higher than the third derivative, you use this. notation here. You could take the fifth derivative by writing it this way, and so on. Alright, let's go ahead and look at a few more examples in from this section. Let's go ahead and take a look at number 10, and I'll draw the graph that's given to us in the book. And so this is f of x. We want to sketch f prime of x. Let's do that in light blue. I want to draw a graph of f prime of x. Okay, well, we're going to look first of all for places where the derivative is 0. There are two places where the line tangent is going to be 0. One is right here, and one you can see is about right here. So for our derivative function, then the y value of the derivative function has to be 0 at those two places. So we're going to cross the x-axis there. We're going to cross the x-axis there. Now, if the original function is decreasing, that means we're going to be in negative territory for the derivative, because the derivative is a slope, and the slope is going to be negative if the function is decreasing. So here it's going to be very negative, and then it's starting to come back to 0, and then it starts to get more and more negative again. So our derivative function is going to start in negative territory, come back up to 0, and then start to get more negative again. Now you can see it's going to be a point where it gets about as steep in the negative direction as it's going to get, and then starts coming back towards 0. So we're going to have our lowest point here, which corresponds to this point, and then we're coming back up to 0. Now at this point, what happens? Well, here the derivative, or the original function, starts to increase. That means the derivative is going to be positive. It's going to be a positive y value for the derivative function, since the slopes are starting to get positive and bigger, so it's going to be increasing as well. So that light blue graph then is a possible sketch of the derivative function of the original function f of x. Alright, let's go ahead and look at number 24 then as well. We have a function f of x, which is equal to 3 plus x divided by 1 minus 3x. We want to find the derivative function f prime of x and the domains of both the functions f and f prime. Well, let's start with the domain of f right off the bat. We can see that this is a rational function. It's only going to be undefined where our denominator is equal to 0. So we set our denominator equal to 0, 1 is equal to 3x, x is equal to 1/3. So the domain of f is going to be all x as long as x does not equal 1/3. If we put 1/3 in for x, we'll get 0 in our denominator. Alright, now let's go ahead and find f prime of x. Well, f prime of x is going to be the limit as h approaches 0 of f x plus h minus f of x all divided by h, which is going to be, let's see, we're going to need more room here, aren't we? We'll see if we can put one line in here. It's going to be, let's come down here, the limit as h approaches 0. If we put x plus h into our function is right here, 3 plus x over 1 minus 3x. So it's going to be 3 plus x plus h divided by 1 minus 3 times the quantity of x plus h. So there's f of x plus h minus f of x, which is 3 plus x over 1 minus 3x, and then all of that divided by h. Alright, should be a fun one. We got the limit as h approaches 0 of, let's see, 3 plus x plus h over 1 minus 3x minus 3h, when I distribute that negative 3 through there, minus 3 plus x over 1 minus 3x, all that divided by h. And so what we can do to simplify this complex fraction, let's just go ahead and multiply both the top and bottom by the least common denominator, so a 1 minus 3x minus 3h and a 1 minus 3x. And so we'll have to do that down here as well. 1 minus 3x minus 3h times 1 minus 3x. Now what happens then? Well, as we distribute on the numerator, it's going to give us the limit as h approaches 0 of the first term. We'll just have our numerator 3 plus x plus h times, we lost this term, so we'll just times a 1 minus 3x. Those quantities are being multiplied together. Minus 3 plus x, and our second term here, the 1 minus 3x is divided to 1, so we have a 3 plus x times 1 minus 3x minus 3h. All that divided by h times the quantity of 1 minus 3x minus 3h times 1 minus 3x. Alright, things are getting good here. Well, let's see, let's go ahead and do some multiplication and simplify the numerator here. We got the limit as h approaches 0. Let's take the 1 through, so that gives me 3 plus x plus h. Take the negative 3x through, that gives me a negative 9x minus 3x squared minus 3xh. Minus, and so let's block this off here. We'll subtract everything we get from this multiplication. Taking the 1 through gives me 3 plus x. The negative 3 through gives me negative 9x minus 3x squared, and the negative 3h through gives me negative 9h minus 3xh. That's it, right? Negative 9h minus 3. Yeah, okay. All that divided by h times 1 minus 3x minus 3h times 1 minus 3x. Oh boy. Alright, so we got the limit as h approaches 0 of 3 plus x plus h minus 9x minus 3x squared minus 3xh minus, distributing everything here, minus 3 minus x plus 9x plus 3x squared plus 9h plus 3xh. All of that divided by h times the quantity of 1 minus 3x minus 3h times the quantity of 1 minus 3x. Now let's see, we should be able to get rid of everything in the numerator that doesn't have an h in it. Positive 3, negative 3, positive x, negative 9x, positive 9x, negative 3x squared, positive 3x squared. Everything else has an h in it. So we have then the limit as h approaches 0 of h minus 3xh plus 9h plus 3xh, all divided by h times the quantity 1 minus 3x minus 3h times 1 minus 3x. Now, I can factor an h out of everything in the numerator here, you'll notice, and that leaves me with h times the quantity 1 minus 3x plus 9 plus 3x. Yeah, we sure can, huh? We have a positive 3xh and a negative 3xh. Is that right? That's right. So those are the 0 and 0 there. So it gives us that divided by, let's see, divided by h times 1 minus 3x minus 3h times 1 minus 3x. So here now the h is divided to 1, and we're left with the limit as h approaches 0 of 1 plus 9, which is 10, divided by 1 minus 3x minus 3h times 1 minus 3x. So it got a little bit messy there. We let that limit go now. This is a rational function that has 0 as part of its domain, so we can plug 0 in for our limit, and we get 10 divided by 1 minus 3x times 1 minus 3x, or if you like, 10 over 1 minus 3x, that quantity squared. And there you have, remember this is f prime of x. That's our formula for the function f prime of x. So we need to find the domain of this new function f prime, and the domain of f prime, well, we're going to have basically the same issues that we had for f, and that is that we can't have 0 in our denominator, so we have to make sure that 1 minus 3x quantity squared, we have to find out when that equals 0. Well, that's going to be only when 1 minus 3x equals 0, which of course, as we said earlier, is when x is equal to 1/3. So the domain of f is going to be the same thing, all x such that x is not 1/3, or if you like, in interval notation, negative infinity up to 1/3 union 1/3 on out to infinity. So that is, again, the domain of f prime, the same as the domain of f. Okay, I want to look at one more problem, and that is actually number 30. Number 31, where it asks us to decide where the function is differentiable, where it's not differentiable. And just to reiterate that, what we talked about a little bit in the last video, where it's not differentiable, you can see it's not going to be differentiable at this cusp right here, because you can see the slope of the line tangent here is going to be a positive, very positive slope, and then we have a sudden change to the slope being a very negative slope, and there's not a nice smooth transition from a positive slope to 0 to a negative slope. So it's going to not be differentiable at x equals -4 because of that corner, or that cusp, that very sharp turn. It's also going to not be differentiable at 0, at x equals 0, and because it's there's a discontinuity there. Remember, in order for a function to be differentiable, it has to at least be continuous, first of all. If it's not continuous, it's not going to be differentiable. So there's another place. Now, it almost looks like we have a third spot where the line tangent is going to be a vertical line, but I don't think we ever get to that place over here where the line tangent is a vertical line and thus the slope is undefined. So I think it's only going to be in those 2 points at -4 and 0, where we have a corner for -4, that's the reason, and a discontinuity at 0, which is the reason for it not being differentiable. Okay, so I don't think you have one exactly like that in your homework, but I just wanted to go over those concepts again of when a function is not differentiable. I think you should be in pretty good shape for your homework, and of course you can always email me or chat with me online if you have any questions about the homework. The password for 2.8 is going to be penury, 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 which means severe poverty. Severe poverty. So good luck on 2.8. Let me know if you have any questions.